So we have to go to Europe, and now actually I don't know where Heidelberg is, so I have to do it here. And so now you see the small spot, and that's Heidelberg. And if you zoom in and go further in, we can go to my lab and see what's happening there, but I will not do this. Okay, so this is University of Heidelberg. It's the oldest university in Germany, which is not very important actually, but the university is proud of it. And I should not make jokes about my university here. So the topic will be atom interferometry. Actually, it's not really what I do, and I also thought it's Friday afternoon, so it should be more entertaining than selling what I'm doing, so it will be more an entertaining story. Somehow I put together, and clearly at the end I will also present what we do. Okay, so I will have a start with introducing classical matter wave optics, which somehow sounds maybe strange because I call matter waves classical. Okay? Because the quantum part of it is the excitation of these matter waves. The same thing as photonic waves are classical, but the photons, the excitations is quantum. Okay? So in that sense, somehow it sounds weird. How can you make classical physics with matter? Because it's always granular. Okay? But the single particle experiments are classical field experiments. I will introduce that, and then I go further and ask, well, what's quantum atom optics? Actually, it deals now with the quantum mechanics of these particles in these modes. Okay? And that actually I will introduce my system or the system we use, and this allows to do new things. New inverted commas, because the photons people have done this before. If you do quantum optics, one of the goals were to do better measurements. Okay? And this is exactly what we are going to do too. How can you do better measurements with matter waves by using quantum optical tools and quantum optical concepts, and that will bring me to squeezed atomic states. Squeezed light, you might have heard, it's a light which has reduced amplitude fluctuations on the classical side, or you would say there are certain correlations in the photons which allow you to do some things better. One example is what you can do better is interferometry. And this is not something which is, well, 20 years ago this was a big thing to show and demonstrate, but nowadays it works every day. There's the detector GO600 in Germany. It's a gravitational wave detector where you measure gravitational distortion or distortion of space due to gravity waves. That's the hope. And you do this by interferometric measurements. And there you already use squeezed light every day to improve the resolution sensitivity of the device. Okay, so now the title was actually atom interferometry yesterday. Okay, this will be this part. Then this was today. Well, today I'm stretching a little bit. It's also the last 4 years. And then actually there was tomorrow too. And tomorrow, I mean, there can be many things. Okay. So essentially, it's a little bit of a question what I will talk about, but I will talk about the things which are already yesterday now, because we have published this. But it's about going beyond the squeezing and showing that you don't have to use squeeze states. You need quantum correlated states and to do better interferometry. And I don't know how far I get. If I get to here, we can also stop here. And actually, I was told that there can be questions in between, and I invite you to ask questions if things are not clear or you want to understand something better. We don't have to go through this full program. It's better I tell you what you want to know. Okay, so everything starts with this relation. If we go to matter wave optics, the de Broglie wavelength is given by a Planck's constant divided by m times velocity, which is the momentum. And typically would say, well, it's small. Yeah. So if you further go and ask why it's small, well, you can connect the velocity to temperature, and then you would say at room temperature, you can plug the numbers in, and then you find out that for rubidium atoms, and that's the workhorse we are going to use, at 300 Kelvin, it's 17 picometer, which sounds like a small distance. As you will see, that actually does not hinder you to see wave phenomena. You just have to do the experiment properly. But since we are lazy, what we are doing is we're lowering this temperature, and if we lower this temperature by some orders of magnitudes, to 13 nanokelvin, well, then this actually gets this kind of number, which is 1.7 micrometer. And then actually you can see it with your bare eye. Well, inverted comma, you have to take a lens, and then you can see it with the camera, but which is almost like bare eye. And this makes this field of Bose Einstein condensates so interesting, especially at the beginning, because you can just look at it. You can just see it, and we'll give you some examples of that. Good. So, when does it start? Well, it starts quite some time ago, and I thought that the first time really the matter waves has been seen was in Davis and Germer's experiments. And I recommend to read this paper. This is the original paper where they showed that the electrons have an electronic wave, de Broglie wavelength associated with it. And if you start reading this paper, it starts like this. And I like this. This is the first sentence. Yeah? The investigation report in this paper was begun as the result of an accident, which occurred in his laboratory in April 1925. So essentially, it was discovered in 2025, and then it goes on what happened. Okay, and what happened was the vacuum broke. Okay, and then they had to do the re-vacuum again. And then you heat up their samples. Because what they have done before, they had taken samples, took electrons and looked at backscattering of these electrons. And they were like spread out. And they took all different samples, you can imagine. Okay. Then he had this accident. And what happened is actually in this process of rebuilding and refurbishing the machine, heating up the sample, they annealed the surface and they got crystalline structure. And suddenly they got these peaks coming out, which were the diffraction of the electrons from this crystalline structure. Okay, so nowadays you would say, well, this is an enormous result, you should stop there and publish immediately in Nature, well, I don't know what, yeah. But they went on and took other samples and other samples and other samples, and that's, I guess, why it took from 25 to 27 that this was published. It's actually a very long paper, and the later part, I think, for nowadays, I think is not so interesting. The first part, seeing this diffraction pattern, was a big breakthrough. And that's actually worth a Nobel Prize, which actually nowadays here in this building, is a good connection. So these are the old Nobel Prizes. This is the latest Nobel Prize. And they got it for this method, this wave structure of the electron. Yes.
So this is all independent from the de Broglie proposal?
That was at the same time. De Broglie wrote his... They knew about it at this time. Because, because de Broglie had his thesis finished at this time. But it was his thesis, which is also an interesting story. So it was his thesis finding that and actually reasoning is also beautiful because you start with A is mc squared, and you start with energy is h bar omega, so you associate with energy a frequency. Okay, so now the next step is to general relativity. You said, well, if you have a frequency associated with a particle, okay, then it depends on the motion, on the reference frame, what you can see. Okay, so you do the Lorentz transformation if a particle is moving. And the Lorentz transformation connects this frequency with space. And it does it exactly the way, as we know, it's the de Broglie wavelength. So it's also a paper worth reading. It's the same time. It's really a very, very interesting story. Okay, so this is actually 87 years ago. So now I would call this yesterday. I also would call this yesterday, although this happened in 1991, and it happened actually in the lab at Constance, where we stayed. And it was about a double-slit experiment. So it was taking helium, neutral particles, exciting them to a highly excited state, make them metastable, and shoot them through a small pinhole. Okay, this was a gold foil with just a cut, and you send it through. And then there were two slits. Okay, and if there are two slits which are coherently illuminated, then you would see an diffraction pattern. Actually, you would call this interference pattern. Okay, and that's what they have measured, and that's where the first results. So if you take slow atoms, and you can do this by time of flight here, if you take slow atoms, you see a big structure. And if you take fast atoms, you might wonder what this is, but in this paper they claim it's also an interference pattern which is fast. Okay, and actually funny enough, the scale is exactly what I showed you before. Also now that the Broglie wavelength is 17 picometers or something like 10 picometers, the structures feel big. And how do you do this? Well, if you have a wavelength and you want to see the interference, doing this is the worst thing you can do because then you get a structure which is as small as the wavelength half. But if you make the angle very small, then you can make it infinitely big. So here the trick was that the angle here between the waves was very small, and so you can enhance this effect and blow it up such that you can observe it with a this is just a channeltron which detects these excited atoms, spatially resolved with a slit. Now this happened, this was received on the 4th of March. Okay. Now, there was a paper on the 7th March received by PRL, which was by the group was Dave Pritchard. So this is Jürgen Lünneck, and this was Dave Pritchard at MIT. And they built this kind of device. So I try to explain this now a little bit more detail. This device here consists of 3 gratings, which again are transmission gratings. And now if a wave comes from the left, and now it's an atomic beam, it's a wave, we know it's a de Broglie wavelength, it will have diffraction. Okay? Now, it impinges on a second grating, you will have diffraction, and so you can imagine there are lots of other orders too, but if you just take those two orders, you see that they recombine here. Now again, there's a small angle, okay, and this angle just means that you have an interference pattern here, which has just the periodicity of this grating here. And so now what you can do is you can read out this interference pattern of these beams by moving this grating, okay. So, that is actually here, and then it was much more sophisticated. You had to stabilize these gratings with each other, and we did this with light fields, and so at the end what they got out was interference pattern like this. So it's a very clean signal compared to this one, but I should not judge this here, but definitely they were published then back to back. This one first and this one second. So at that time it was an exciting news that you can do interferometry with atoms, and I remember when I was a student, well, my supervisor for my diploma thesis came and said they see interference with atoms, and I said, I don't believe that. But now it's relatively settled, and this is actually still in yesterday, so it's 23 years ago. Now it moved further, so just showing the effect is one thing, but using it is another thing, and if you can use it for something sensible, it's even better. Okay? So one step was using this interferometer for measuring gravitational acceleration. This was done in Stephen Chu's group, and Achim Peters was the leading postdoc there, or PhD student there actually. And so what you see here is an interference pattern. It's a little bit more not done in a different way of reading out. It's not so important. It's the same thing as before. It's a 3-grating interferometer, as we have seen before. So essentially, it is this kind of configuration, and what this oscillation here is the output of this of this output here as a function of moving this grating. And now we can ask, what can you do with it? Yeah, here's gravity. So what should gravity do? Well, gravity, in this case, points downwards. What it will do is it will bend these beams of the atoms. And so what happens actually is the angle will not change much, but where they hit the third grating will change. That means this periodic structure which you produce by two beams impinging on each other will move. Okay, so now if this moves, then you get this image, and that's it. It should be always the same. And then they did this for 2 days. Sounds like a boring job. They'll just do this experiment, 2 days, and measure this kind of pattern. And what they found out is actually this pattern is not constant. This pattern is moving. It's moving up and down, yeah, in a period of 1 day. Okay? So what this means is gravity has to change over time, because that means it's pulled more or less. Okay? Now you can calculate how much this difference in shift of this pattern, what this means in change of gravity, and it turns out, well, it's 3 times 10 to the minus 7 g. This is a small scale, but you have a very good ruler too, because the atoms have a good, form a well-defined inertial system, and you can compare it to different gravitational accelerations. And actually it turns out, and here are models, the difference to Earth models, that this is actually exactly what you expect because of tides, changing of the Earth crust, and things like that on a periodic basis. Okay? So this shows you that this is actually a very precise experiment. And nowadays, I know Achim and also other people, like Philippe Boyer and Mark Kasevich, building these devices. And Philippe Boyer having a company, you can buy this device now if you want. It's a little bit expensive, and it's not going for the mass market, but you can buy it in principle. Okay? But essentially, all it is measuring how things drop, but you do this with a very fine ruler, and so you can measure very precisely. So that is actually 15 years ago, so now we're getting closer. So now if you look at these beautiful results, and they analyzed what the position of this pattern is, if you look at these results and you zoom in here in the front, you see these kind of data points and this line which is the theoretical expectation. And then you might wonder, well, it's a precise experiment, why is this point off? Okay? And I will show you it has to be off. Yeah? It has to be off. It would be on line, there would be something wrong. Okay? And that comes now in the following. So, and this brings me also to what we have done some years ago. How can I make sure that this point is not here, but it is more on the line? That's now the name of the game. Okay, so for that I would like to introduce interferometry and need some concepts to show you with aerobics what's happening. Okay, so Mach-Zehnder interferometer is an interferometer where you have this enclosed area here, and I showed you this before already. We call this external because it's in the motion of the particles. Okay, and this is an example we have seen before. Now there's another one which is an internal interferometer, where you have, it's called Ramsey type interferometer, which is actually basic for all our time standards, which is, instead of going left and right, you are going spin up and spin down. And so it's a two-level system, it's the same thing, we just call it differently. Okay? So essentially here, an interferometer works like this. You have first a beam splitter, you split it into two paths, and then you recombine it at the last one. Here you do the same thing. You start with one state of the atom, bring in the superposition between two states, let it evolve, and then do again a mixing between the two states, and then you get either up or down, or red and blue. Okay? And whenever you have two states, what I'm going to tell you, you can use. Okay? It's very general, and so you can find it in many different contexts. Okay, so now how does it work? We start with single particle interferometer. We start here with a particle coming in here. Okay? And then it splits. And then in the external case, this would mean you start here. It can realize this with a double well. Here at this point, the particle will be left and right. So it's superposition between left and right. And out here, well, it can be either right or left again. So now for the internal degrees of freedom, I just repeat what I said before. This left we call spin up, the upper state. This is a superposition between the two states, and it's the lower state. So the most general state you have is a superposition between the two states. And since they have only two numbers, which are the relative amplitudes and the phase, you can represent all states on a sphere. And this is called the Bloch sphere. Okay, so now the Bloch spheres I'm going to use for my explanations. So if you're in the upper state or on the left side, I call it spin up. And if you're on the right side or spin down, you call it down. And we know spin up and plus spin down gives spin in x direction. Okay, this is the weird thing that if you add up two spins, it goes in the opposite direction. But the spins are never up and down, they're always like this, so this adding up of spins works. And so essentially on the sphere, all on the equator here are states which are superpositions between up and down, and the angular dependence here is the relative phase between the two states. Okay, so now interferometry. What is interferometry? It's nothing else but this vector describing your system makes a path in configuration space. And it does it in a very special way. So we start first with being spin down because everything is left. Okay? Now, if I do this on a particle, I will find the particle on the left-hand side. Now, if I do a new experiment, I will find, with 100% probability, it's on the left-hand side. So if I repeat the experiment many times, I will always find the same result. So it's an eigenstate of being left. Okay? So now we do this beam splitter. A beam splitter actually makes a superposition between left and right. So this vector somehow have to go up to the equator. And it turns out that it's just a rotation around the x direction. So essentially what happens here is the vector rotates up to the equator, as shown here. And now the result will be what? Well, the first experiment will be left, the second right, the third right, and so on. And actually each of them you cannot predict. You don't know what the outcome will be. But you know on average it will be 50-50. Okay. So now you just let the system evolve. And if you let the system evolve, this part, which is the left part, gets a phase. Okay? It's maybe a different energy, and so you accumulate phase. So now if you add spin up and spin down plus a phase, what you get is a vector in equatorial plane, but shifted. Okay? So all what happens here in this explanation, in this picture is the vector rotates around the equatorial plane, and this phase phi you want to infer from your measurement is actually this rotation of this vector from here to there. And if you do now the measurements again, you see no difference. You don't see a difference between this and that one. It's again 50-50 chance that you are left or right. There's no information in this measurement yet about the phase, because you measure particles. And that's the only thing you can do. You can count particles. You never measure a phase. You count and infer the phase from your counts. Okay, so now if you want to measure this phase, we have to map this kind of angle to something we can measure. And what can we measure? We can measure how often is a particle left and how often is it on the right. So we have to get this phase onto the z-axis, which is the measurement axis we can do. And actually this we can do because we have done it already once. We moved the z-axis to the x. So we can do the same thing again backwards, and we will map now this vector to the z-axis. And since it's rotated, it will not go down, the original one, it will go up to another level. Okay, so if it go up, it goes down, and then I go down. Okay. So now this I can measure, because now it's not pointing downwards, it's pointing a little bit up. And that means the probability that you're left is still very high, but it might happen that you're also right. With a certain probability, and the probability function is given by the sine function. So actually, if you want to read out the phase, what you use is that the particle number difference between the two outputs here and there, on average, has this dependence on the phase. So essentially, this is the explanation why this point is not on the line, and it's not allowed to be on the line because it's statistical. You have to have infinite many measurements in order to have this point exactly on the line. And infinite is a big number. So essentially, now the question is, can you do better than this kind of statistics? And that will bring me to the squeezing. Okay, so how can I do this better? If I do the experiment n times in a row, each experiment will be the same. I cannot do better. It's just like adding up statistics and I get the square root n fluctuations. But I can try to explain this on this sphere, what I have to do. Because if I have one particle, I told you it's one spin. But if I have many particles, I will have many spins. And so all I have to do is, I have to add up these spins. But since these spins, if they're independent, are not correlated, you will get some uncertainty. Okay? And this uncertainty will limit you, because I told you the interferometer is measuring the phase by measuring particle number differences. So essentially what you want to know is how, if you have a vector, how well can you distinguish it from a little bit shifted? That's interferometry. And you want to know it as precisely as possible. Because then, if you have the angle, you know the phase. And the phase might be connected to things you are interested in. For example, I don't know, time differences, frequency differences, or I don't know, pressure, whatever. Okay, so if we add this up, we get this uncertainty. And if we add more up, the uncertainty will grow. Okay. Now the area here will grow with n. The higher I make the particle number, this will get bigger and bigger and bigger and bigger. Sounds like a bad thing. But the sphere also gets bigger. Okay? And now I am asking the question, how well can I resolve it? Well, then it's a question of areas. I have to compare the area of the sphere with the area of my uncertainty. And this is on my side. Because the sphere grows with n squared, while the uncertainty only grows with n. And so you're better off to measure more to get more precision. And we all know it's a photon shot noise, or it's not shot noise goes down. You can average it down if you take more and more experiments. Okay, so now doing more and more experiments is not how you get out, because in this experiment I told you this was 2 days, they did lots of shots, and there's no way to do more. So the question is now, you have the number of experiments given, how can I do better? And from this picture, actually, it's suggestive, because you would say, if I'm able to correlate these spins, these vectors, such that they form a big vector which looks like this, so the uncertainty in this direction is smaller than in this direction, then it might well be that then it's actually very obvious that you can measure rotations perpendicular to this, or rotations in this direction here, you can measure much better, because the uncertainty is small, and so you can measure the difference. And that's obviously squeezing. Okay. Good. So now, how does this show up in the experiment? Suppose we take one of these very special squeeze states. So if you think about it, we want to make this uncertainty as small as possible. Okay? But as I showed you, it's a sausage physics. You compress it here, it expands in this direction. Okay? So, yeah?
What you call classical is just the uncertainty on a Gaussian distribution?
Yes, I would call this classical. Yes, yes. Exactly. That's for me a classical state. A coherent state is the most classical thing we can think of. It's like the coherent field of an electromagnetic wave. Yes, absolutely. Okay, so now we take a very extreme case which is not classical. So we squeeze it. Okay, so now what is an interferometer? Interferometer is rotating this ellipse and measuring particle number difference, which is the Z component. Okay, so now we rotate this, and this would be 1/2 fringe. Now what you measure is, well, you measure single results, but what you plot is averages. So then you have to ask about what's the expectation value of this vector, and it's not as long as the sphere anymore, it's smaller. Because it's bent around the sphere, and if I ask what's the probability, if I add them all up equally, what the length is, it will be shorter than being at the top. Okay? So the length of the vector gets shorter, and this means the mean value, the observed mean value difference will be also smaller. And we call this visibility, right? So in this case, if this is the maximum signal you can have, if you have this kind of state, you would see that you have some modulation, obviously. because here you have none and here you have maximum population difference. But the visibility will be reduced. But you also have small variances here in n. Okay? So the variance in n is also small. But you want to infer the phase. And that means you have to know from this uncertainty how big is the uncertainty of the phase. Well, and shown here is this uncertainty. Now, if you take another state, which looks a little bit worse, yeah, it's squeezed but not as much, then you find out, well, actually now the signal is bigger, the vector is longer, so the signal is bigger, the error bar is bigger, because this variance here is bigger than the yellow one, but the phase estimation is better. So at the end of the day, for every experimentalist, what matters is signal to noise, and not only noise. If the signal goes down and noise goes down, it doesn't help you. Okay, so actually it's a balance between how much of phase do you lose and how much squeezing particle number suppression do you gain. And so actually this was Dave Vineland, also Nobel Prize winner. Wow, it's crazy, they're everywhere. Yeah. He came up with this criterion and showed what's important is that you show that the variance of particle number difference is small. That makes very much sense. But what you also have to show, this term here measures the length of the vector. And it's called coherence. So you have to show that you get a nice interference fringe with small variance. So if, as an experimentalist, what you have to do is you have to produce a state where the variance of particle number is small and the phase coherence is still there. And this is a bigger challenge that than one might think. Okay. So now, with that, we would like to do this. And the ingredients I already told you. What we need to do is we have to get these vectors doing something in common. They have to get correlated. And how do you get something correlated? Well, if you don't talk to each other, then you are not correlated. But if you talk to each other, you can say, well, let's go together. Okay? So you need interaction between the particles. And there are different ways of doing it. There are people using atom-light interaction to get interaction between the atoms via the photons. Oliver is working on things like that. And Leonardo, actually I should thank Leonardo very much for making this happen that I'm here. Thank you very much for that. I'm sorry, I've forgotten this at the very beginning. You should get all the credit here. So we need this interaction. Okay, and we have chosen the way that we don't go the way via photons, but we stick to the atoms. Because atoms collide. And if they collide, they definitely know from each other. And the question is, can you do squeezing with that? And so one way of doing it start with a Bose Einstein condensation. And I will tell you shortly about this condensation. So well, the phenomenon is relatively clear. So you take bosons, you cool them down, and at a critical temperature, you will get a macroscopic appropriation of the ground state of the system. And so now this is actually the question, why is it hard or tricky to do? Because the main problem here is I draw these circles and I draw these Matterwaves. So I'm thinking about single particles moving around. And what happens if you cool down things? Typically a gas doesn't stay a gas. It gets a liquid and then it gets a solid. And so the challenge is, how can I get these kind of quantum states, which would be a good starting point, and not a solid? Okay? And where does the solid come from? Well, the solid comes from these interactions, which I want to have. Okay? Because if three particles come together, what happens is, well, two form a molecule, and the other one takes the binding energy away. Okay? This is the way, this is the start from getting a liquid and then a solid. You form these kind of compounds. Okay? So that means the whole process going from here to there cannot be tuned by density, because what you have, maybe I should repeat that, if going from here to there, what you have to do is you have to get the de Broglie wavelengths as big as the interparticle distance. And there are two ways. One way is get lots of particles close together. Okay? This does not allow you that, because essentially if you bring them together, it's a liquid. So you have to make them apart. But if you take them apart, you have to make the de Broglie wavelengths long. And de Broglie wavelengths long means low temperatures. And actually this is the problem here, so you're density limited. You cannot increase the density too much, because then you get the solid. And so you have to go to temperatures of 100 nanokelvin. So where I started from with this 50 nanokelvin is a standard temperature you need in order to get these states. And then you have to pick the Broglie wavelengths for free. Okay, so now how do we get there? Well, there is this nice logarithmic scale, typically shown. You start with room temperature, Then you want to go to here, which is actually bridging quite some orders of magnitudes here. So you get from 300 Kelvin to a few hundred nanokelvins. And you can, there are different ways, but the way we are following is we take laser cooling, and then you can cool them down to temperatures which bring you about to here. But then actually bridging the last gap was a big issue, and the solution to that is what you most likely have heard is evaporative cooling. You just throw away the fastest particle slowly, this rethermalizes, and if you do it slow enough, then you get a condensate because you can cool down the sample to very low temperatures. Okay, so now since this Nobel Prize is everywhere, I thought this kind of graph you might plot differently too. If you look at this graph, it's very interesting that actually for this kind of temperature, there was a Nobel Prize. This was for the PEC. But also for this temperature, so 4 orders of magnitude, temperature change gives you a Nobel Prize. That is suggestive. Because there is also one. There's also 4 orders of magnitude. Kamerlingh Onley's got one of the first ones because of liquefying liquid helium. And guess what? There's another one here. Another 4 orders of magnitude for the processes in the sun. Okay, so typically I stopped here, and then at a certain point people told me, well, this is not the full story. And this is true. Because there are lots of other Nobel Prizes you can put in here. And actually you can get even for a whole range, you can get the Nobel Prize. So at the end of the day, you just have to do good physics and then you might get it or not. Okay, so with that, we go back to our condensate. And actually, if you look at that, it looks a little bit strange. And it's not drawn wrongly. It's exactly, it should look like this. It's not a Gaussian. But we know the ground state of a harmonic oscillator is a Gaussian. So if I put particles in there, and they are not interacting, it would be a Gaussian. But this is exactly the case. They are interacting. And this is the interaction we are after. We need this interaction in order to produce our correlations between the spins to get the squeezing. Now the nice thing is that in this regime of these very low temperatures, the interaction between the particles is very simple. Because the problem looks like this. You have 2 particles, they move against each other, but this moves very, very slow. So you can associate with this particle at the Broglie wavelengths. And I told you already, it's micrometers. So it's a long wavelength here. But the collisions between the 2 particles will happen at a very short length scale. So this happens at 50 Bohr, and this is to 20,000 Bohr. So this is actually, if you take this interaction potential, make this 1 meter, then the Broglie wavelength is about 400 meters long. So you have separation of length scale, and this is typically nice because then the descriptions get simple. Or you can do good approximations. And so at the end of the day, for the physics out here, remember, this is 400 meters in this direction. The details in this 1 meter here, which are shown here, are not important. But what is important here is that you have excluded volume. So there is a 0 crossing here. Okay? And so this length scale is called scattering length. And so at the end of the day, what boils down to is that this whole interaction, which is highly complicated in detail, you can simplify and describe in first approximation, in a good approximation at these low temperatures, as scattering from a delta potential. So you have contact interaction with a certain prefactor. Okay? And this actually now depends on the scattering length, these microscopic interactions, if this is repulsive, i.e. the energy goes up, or the energy goes down, if A is negative. So in our case, A is positive, and that means it costs energy to put particles on top of each other because of this contact interaction. And so what happens is the particles minimize energy, and so they minimize interaction energy, and with that they go out in the trap. And at the end you can do is also formally can show what you get here, this distribution intensity is just the inversion of this parabolic potential here. Okay, so it shows like this, all these condensates are interacting, although they're called weakly interacting, but weakly interacting in the sense of not forming molecules. But the interaction energy is always, very often, almost all cases, bigger than kinetic energy. So the interaction is there, although they are weakly interacting. Okay, so now we have it. So this is more or less what we need in order to build the experiment, but we need the experiment. Okay? So now what does it look like? And actually this is the first experiment we have done in Heidelberg when I came there, and this is now what we have now. Okay? And it's amazing, huh? It's not much things change. So this is I call this high tech. It's just a Verdi laser bumping a titanium sapphire laser. Costs, like a Lamborghini. The design is horrible, but the Lamborghini is a much nicer design, but you cannot cool the atoms with that. So this is I call this high tech. Then you have some optics. Okay, this is all standard, and you know this very well here. You use this all the time. And then you have these very important things, this cardboard box here, for example, or this plastic tube here. And this makes the experiment working. And that's a good experimentalist combines high tech with low tech in such a way that you get to your results. Okay, and this I think is a very important thing. I mean, just buying does not help. You have to improvise and solve solutions to step forward. Okay, so now 2014. What do we have? We still have high tech. It's still the same. Just another picture. The optics still looks the same, and all what happened is actually this cardboard was substituted by this aluminum box. Still low tech, but now it looks nicer. Yeah? Okay, so now the other side, this is typically the light you need in order to cool, manipulate the particles. You have the other side where you need good vacuum. You have 10 to minus 11 millibar. It's kind of the best vacuum you can get, so without going to helium temperatures, in order to decouple the atoms from the environment. Because you can imagine if they are exchanged with other particles, they will heat up and they will not reach 100 nanokelvin. Okay, so you need good vacuum, and that typically looks like this. You don't see the vacuum and you have some stuff around. Yeah? But now if you look at these two pictures, now this is 10 years later, and you would say this is a step back. Yeah? There's much less stuff here than here. It looks. And this is important. What I'm going to tell you is about stability. You have to make things robust and stable, and this machine runs 24 hours, 7 days a week. Now. And we need that because we have to do many experiments and do statistics on the experiments, so we measure noise. And reduction is the secret. So whenever any experimentalist here, reducing, getting rid of all the knobs you don't really need is an important step forward to get something robustly running. Okay, so amen. So that is the experiment now, and then actually everything happens in here. There we trap the atoms, and they are in this glass cell, and then we cool them down and manipulate them, as I will show you. And the nice thing about these setups is that you can directly look at the atoms because you can do absorption imaging. So you shine a resonant light beam onto this cloud, and then actually it redistributes the photons. So you get a shadow, and you can image this on a camera. And this is a false color camera, and you can see here the imaging was not properly aligned here. So here are lots of atoms, and these are just fringes from the optics. And this comes from the fact that the atoms cloud is very small. It's actually below 1 micrometer, and so you would expect these diffraction orders because the resolution of this imaging at that time was about 3 micrometers. Okay, so now we can produce the cold atoms, we can look at them. Now what do we need? We need the spin somehow, right? Because I need these two things, and I would like to have particle number difference suppression. So how do I do that? Well, what you take is the possibilities you have by forming arbitrary potentials, and you build on that the atoms interact with light. And all we have to remember now and know now is that the atom you can deal with in a dipole. And if a dipole is excited by electric field, you can have it in phase or out of phase. And then actually, if it's in phase, you will minimize the energy because it's d times E minus at high intensities. Okay? So essentially, you can just translate intensities into potentials. And then it's just like what kind of solutions you prefer, what kind of intensity distributions you want in order to reach your experiment. If you take 2 crossed laser beams, you get a harmonic trap. And if you take interference beams, we had this already, you have a periodic potential. If you add them up, you get a double well potential. Now, the double well potential, you can condense into that. You can look into that. Now, one nice number is here. We can measure these. These are 500 particles plus minus 5. This is the error, which comes from the fact that the shadow itself has noise because it consists of photons. So a shadow is never a number, it's always a mean number plus fluctuations, and thus this gives you uncertainty in the estimation of the atom number because of the fluctuation of your shadow. But now we have this situation, left and right, and particles. That's all we wanted. And all we have to do now is, well, hope and try to see that actually the fluctuations between left and right are smaller than square root n. And that's our scale. So we have to get the system stable enough that we can see if you have 400 particles left, 400 particles here, that we have 20 particles, we can distinguish if dental particles on the left or not. And with this resolution we can. But in order to compare your results with theory and predictions, you have one experiment is not enough. Because you have no theory who predicts you how many particles are here or there. It's intrinsically uncertain. So what you have to do is you have to do many experiments. And that's what it looks like. So these are all different experiments. Each of them took 40 seconds. And they are different by this shot noise. Actually by hopping particles left and right on the level of square root n. But actually it's a little bit better, because if you analyze it carefully, what the particle number difference here is, you will find that this ratio here is 0.3. And you remember, this is the parameter of Matterwave and you want to have it small. So this is good. 0.3, it means you are a factor of 3 below shot noise. Shot noise is if you would have them independently, left and right. But there is this other part I told you. Only fluctuation suppression is not enough. We have to have, yes?
You have a kind of a optical lattice with a BC there.
Yes.
Okay? And you let them interact between the nearest part.
Yes.
This is where
Yes.
you are looking only at one pair. Is that right?
Yes.
Okay.
Okay, this is done in a way that there is only one pair. So the lattice is there, but you have the harmonic trap, and the harmonic trap shifts the outer part so far off that you get a double bell. So there are only two there for this experiment. Yes. Okay. And actually, in order to get this number here, there's still hopping is allowed, but interaction is there too. And since it costs you energy to put more on one side, the hopping is suppressed, because it costs you energy to go there. So particle number is suppressed because of interaction. And now the question is, what's the relative phase? Because that's the important part. This parameter here tells you how well is the phase defined between left and right. Okay? And this we have to measure. And now the question is, how do you measure the phase between this blob and that blob? And what you do is you count. And if I count, I cannot see the phase. I measure psi squared. I measure how many particles left and right. You have to do this mixing again, as I said before. The last beam splitter is necessary. What means beam splitter? Beam splitter means part of this cloud has to go to here and part of this cloud has to go to here. And the good thing about this is you don't have to do this explicitly. All you have to do is switch off your trap. Because if you switch off your trap, I showed you this gravity measurement, it will drop. If it drops, it will expand. And if it expands, we do the experiment of Munich, but now with n particles. Okay? So actually what we expect is that we get an interference pattern, and also here we expect to see an interference pattern. And voila, you get an interference pattern. So now where is the visibility? Well, if you do an experiment again, the interference pattern will be a little bit different. And if you do it again, a little bit different. Because again, the prediction is about averages, ensembles. So we have to do many experiments to compare to theory, and so we do this. And then what you see here is there's many experiments next to each other, and then you average that, and then you get a visibility which is reduced because it fluctuates a little bit. And it's this visibility which matters, because if you want to measure a phase, you have to repeat your experiment over and over again. And the single visibility does not count, because it can be 100%. But the average is needed in order to extract the signal. Okay? So this is the visibility, and it turns out, well, we are lucky, this number is not too small, it's 0.8, and so 0.2 divided by 0.8 is smaller than 1. And we are happy. And we were very happy. It cost us lots of time to get this going. And what was the main problem was temperature drifts of your system. Okay, and the solution to that was a massive aluminum block of 30 kilograms, and put it there, and then it was solid enough and coherent enough that one can see it. Okay, so now we can summarize this experiment. I'm not going into detail of these data points, but what you see here is this green line. So everything below this green line means the fluctuation is suppressed compared to the classical one. And in this direction, you have the phase. Okay, and these points here below the orange line, which is the line Dave Wineland introduced, allows you to do improved interferometry. And so if you look at this line, it's about 3 dB. 3 dB is a factor of 2. Now this is inferred. And I would like to make a distinction between inferred and measured. Inferred means that these numbers, they are solid numbers, but not usable. Because if you want to use them, you have to do an interferometer with all its kind of drawbacks, not perfect alignment and things like that, and then see what you get. And not only your input state. Okay, that's the input state. And then actually, all this kind of things you build up over time says 3 dB is not enough to see something. Okay. Yes?
What is the free space in the tower?
But it's about, this is 6 micrometer.
From the up one.
Huh?
The scale?
No, it's another scale. This is another scale. Yeah, it's another scale.
And what is the
Oh, I don't remember. We can calculate it. We just need the relative velocities between the two, I don't know.
What determines the fringe spaces?
It's the angle.
But also depends on some wavelength. I mean,
Yeah, it depends on the relative wavelength velocity in this direction, which gives you the interference pattern again. So essentially, you know, they drop. Okay, so this component in this direction stays the same, but as you go down, they just accelerate. So this pattern actually stays about the same. And essentially, well, I don't remember. It's a long time ago. I've forgotten. It was most likely something like 10 milliseconds dropping, or something like this. But this scale is big. I mean, we can go through, if we want to extract it, we know that pixel size is about 2 micrometers, and now we can count the pixels, and then we are about, 40 micrometers or something. Okay. Yes.
You put up the conjugate variable phase.
Yes.
Now,
Inverted commas.
Phase has to do with number.
Yes.
You are squeezing number.
Yes.
What is not being squeezed? The opposite. What's the complementary that's not being squeezed?
Cos phi. Cos phi. Cos phi. So cosinus of phi. That's why I say phase is inverted comma the conjugate variable. It's an approximation where you make sine phi equals phi. So the conjugate variable for n is phi in the approximation that the phi is well defined.
So the upper bound is 1.
Yeah, but this is, if you go to the limits, it's wrong. And we can do this, okay, now this is actually an important point. I think it's more important than the other stuff. So, the phase is not an observable. Okay? So, essentially the right thing to talk about here is the spin. Because for spin, we know everything. So we have this big spin, and there's a quantum mechanical big spin, which has an x, y, and z component. But we all know that there's a commutation relation of x, y commutates to z. And this also implies that the variance of x, the variance of z, is connected to the mean value of z. Okay? Or y, mean value of phi. Okay, and this gives you the right uncertainty. Also in the right limit, if n goes to 0, what do you do with delta n times phi? Equals bigger than 1. If 1 is 0, it's 0. But there the approximation of phi is wrong. Because the approximation of phi says the fluctuation of this thing is small. But if delta n is 1, the phase uncertainty is 2 pi. And then the approximation is wrong. And so the phase is not a good concept. But cos phi is the right concept. Operator. And I like it actually better because this is an n-particle system. This collective spin, it's called Schwinger representation, is the right thing to do. And then everything is safe in the sense of all uncertainties are the uncertainties you know from angular momentum. So we know also like for a spin and a half, well, you can have the length and the z component, but not x and y. This uncertainty boils down to this uncertainty here. Yes. Now, because I think this is a very good system where one can explain what means, what this uncertainty with phase should be, and at what point conjugate variables in sense of n and phi are the right ones.
Higher angular momentum is a problem because of the phi complementary.
No, with angular momentum you are safe. You can do everything is right. There it's...
Now my question, if you have x and p,
Yes?
linear momentum, both go to infinity, then you're okay. But you have angular momentum that goes around.
Yes?
With phi, the complementary. That's where there is a problem, it seems.
I don't see it's a problem.
Well,
No, what do you mean?
I can ask you what.
Yes. Yeah, no, for this system, this angular momentum representation is the right one. And the phase is the wrong one. But I use the phase because you have heard the phase before, and the angular momentum not. The angular momentum is the proper one. One can make the connection, but I repeat, the connection is in certain limits. And this is also what somebody asked, a classical limit. This kind of n and phi are the right variables. That's why it is, like a Fock state has no phase. Yeah. But still it is represented by one of these spins. Okay. So, yes. So essentially, this is good, but you cannot do an experiment. So why is that? Well, and then if you actually look what's possible, it's scary. if you ask what's in principle possible with this system, you would expect about 30 dB squeezing. And this is 1000. So I lose everything from 1000 go to a factor of 2. And why is that? Well, the whole thing is I started with t equals 0. And this is wrong. Nothing is at t equals 0. You always have finite temperature. And this finite temperature will limit you, and that's actually consistent to these values. So if the temperature limits you, there are two ways out. One way is you lower your temperature. That's the easy way. But for us, not possible because we are already the lowest temperature we can reach. So what else can you do? Well, you can start to decouple your system, make the energy difference of your system bigger, so that you have no excitation of the excited states anymore. Okay, so now you can imagine motional degrees of freedom are very low energetic. So I need something else which have higher energetic difference. And for the atoms, that's very natural. What you can do is, you cannot use just the external degree of freedom, but the internal degrees of freedom. And the internal degrees of freedom here, this is 6.8 gigahertz, which is enormous. And temperature-wise, I have to heat this up to high temperatures to break this. So essentially, if I go to this internal degrees of freedom, temperature is not an issue. Okay, so we did that, and it turns out, well, we get this value. Still, you would ask, why is it not lower? This value is already quite good, but it's not lower because we have this molecule formation, as I showed you. We don't have switched it off. We have just suppressed it because the density is small, but it's not 0. So we will lose the particles. And if you have something, you have something where the particle number difference between left and right is 0. So we have here 40 and here 40. And you lose a particle. You lose it either left or right, not together. So if I lose that, I have 40, 39. Okay? And now I have already, if this happens randomly, I will have the particle number difference fluctuations which go to the shot noise limit again, a non-interacting case. And this kills this squeezing. Okay, so now if you have that, and it's a good resource, you should do this interferometry, and then I'm finished. So if you do the interferometer, this case is now in internal degrees of freedom, so it's the sequence I introduced for the time standards. So you start with one state being in one input port, make a 50-50 superposition, wait a certain time, make another mixing between the two, and then do the readout either up or down. And the interference fringe looks like this, as Achim Peter's experiment. It looks like for different phases, the signal goes up and then goes down and up. And if you want to infer the phase, you want to know where you are here, you would not go to the maximum, obviously. Because if it changes a little bit, the signal does not change. You would go to the steepest edge here. Okay? And this here is a zoom in. So this is a zoom in into this part here. It's a zero crossing of this fringe. Now we can zoom into that too, again. And then what you see here is there are lots of points. And each of these points is one experiment. Okay? So each experiment gives you one result. But essentially what Achim was plotting, he also had many experiments, he was plotting the mean. Okay? The mean has a certain error coming from these fluctuations. Okay, so now what you see here is the fluctuations. You see the 2 sigma bar. This is from the experimental data, the blue lines, and the gray shaded one is the experimentally expected, the theoretically expected one, shot noise limit. The best you can do. At the best interferometer, 100% visibility, these fluctuations will not go away. So actually we're not so bad, we are close by. Now you do the same thing, but you introduce a squeeze state into this thing. So you do first the sequence of squeezing it, and then you get this result. So on this side here, it looks similar. A little bit worse even. The visibility here is less. But remember, we expect that. If we squeeze it, we expect less visibility, because of this vector gets down. But the error here should be better, because now the fluctuations are smaller. So here is a zoom in, and we just shifted it in order to show it better. And now here you see again many experiments, but now the 2 sigma bar is smaller than the expected one from the best interferometer. Best interferometer with non-interacting particles. And so here you can see clearly what squeezing means. Squeezing means you lose visibility. You see this is not as steep as this one, but the variance here gets faster small than the signal goes down. Okay? And so now from this one here you can infer the phase better, because the phase is actually now this uncertainty here. And this is smaller than this one here. Okay? And this was the demonstration first time for atom interferometry to use squeeze states and go beyond the classical limit. Okay, and now this brings me back to this point here, as I said. This point has to be off, because it statistically has to be off. And in order to get it closer, you have to use these kind of resources. Or you average longer. And sometimes you don't have enough time to average. And that's when these things might kick in. Okay, so actually I think I should more or less finish here. Then I skip the other part, and we can have a discussion. Okay, so with that, I thank you for the attention. What I told you is that we can do this squeezing in external degrees of freedom. We can do this in the internal degrees of freedom. And what I didn't have time is to show you, you don't have to stick just to the squeezed states. You can also go to this kind of strange states. And they also have resources there. They're actually a little bit better than the squeezed states, if you could use it. And how to use that is by itself a whole story. Okay, and with that, I thank you for your attention.
Thank you very much, Markus, for this very inspiring talk. So I saw two questions. I don't know which first, maybe you.
Yeah, of course, so it's a whole story, but could you give us a flavor of it? Just
Yeah.
3 words, only 3 words.
3 words. Oh, but. Let me see. Okay. So given you have this thing. Okay, actually it's not so understand. So I told you that this interferometer is shifting around the states around the sphere. And you would like to know if it's here or there. Okay? And this is, the simplest approach of error propagation and estimating from your experimental result what the parameter is you want to know. Because you say, variance is describing everything, and the mean is your signal. But this is the most simple way of analyzing your data. You can also ask, what's the probability that the measurement set I have corresponds to this probability distribution function? And for Gaussians, it's enough to have the second moments. But if you have more general things, you have to ask how likely, and this is called about the maximum likelihood estimation, how likely is it that my measurement is consistent with this parameter? Okay, and this is what you have to do in order to use this kind of resource. I don't know if this was now, okay, it was not good. Okay. Because I have there 2 messages. One message is that if you extract from experimental data a signal, what do you mean with signal? You mean you make a connection of the observations, which are typically photons in your case, right, to the parameters you want to estimate. And then actually you have to calibrate your device. Yeah? You have to know if I have this measurement, I have this result, or I have this parameter. But this connection is typically not one-to-one. Typically it's such, if I have this parameter, I have this kind of distribution. And if I have this parameter, I have this kind of distribution. So at the end of the day, it's a question of, you make measurements and ask, the measurement, is it from this distribution or that? Now here you see immediately, if I take the mean and the variance, it's very bad. This is absolutely uncertain here. And I take this one, it's also bad. But clearly you can distinguish this from that. But in order to analyze that, you cannot do this with variance analysis. You have to ask, how big you set, how consistent is it with this distribution or that distribution? And this is the maximum likelihood estimation. And if you do that, then you can show you can use this state. Actually, we did it the other way around, as you know maybe. We did exactly show that this allows you to measure better phase, and with that we could show that this is entangled. Yeah. I think there was a question over there, and then you had a question, right? Yeah.
So you're looking at the pair because we're basically doing an interferometric measurement and looking at the squeeze, okay? Can you still see squeeze if you have like a diffraction measurement instead of a pair? You have a bunch of bases, and can you still observe squeezing with that?
Yes. I'm thinking about what kind of squeezing you mean. Indeed, because now there are different regimes suddenly. Huh? If I have many of them, what do I allow, what do I not allow? Okay? So, if you allow that they hop, and actually also what we could show experimentally, you can have 6 of them, and the number of fluctuations each of them is suppressed. And also the phase fluctuation between each of them is big enough that everything is squeezed. That's possible. Okay? So now, but it depends on your parameters. You can easily have you're locally squeezed but not globally squeezed, and then, so let's put it this way. Going back to experiment, we have shown that 6 sites actually are particle number suppressed fluctuations, and if we had phase measurements between them which were entering in this experiment. And so they were squeezed. But this was a regime where they were all coupled together. And the latest thing that we have done is, if you take this squeezing now in internal degrees of freedom in one of the blobs, then you're limited because again, as this free particle loss kills you, you cannot put more particles in. And the main challenge is to have bigger systems with this squeezing. And so now what we did is we did 40 of these condensates next to each other. And all of them were squeezed. So if you take the whole sample, it's also squeezed. That's what we have shown just recently. But this is independent squeezing. It's just adding up squeezed samples gives you a big sample which is squeezed. And now you are asking more, I think, which is about, because now we can start chatting because there are lots of things to do. You can ask then, what about EPR correlations? And there should be EPR correlations if you start to do more wells with these systems. So meaning, if you know this spin is up, we know that this one is also up. There is some correlation. Okay.
No, in this case it's model 3 because model 3 you take the system and you add a model. You say I change this parameter. In this case phase. This is another input. And then you do this for different phase imprinted. And then you check how
fast does it depend on this phase. And then you can see, well, I can estimate this phase better than classical possible. Okay. But it's right, you have to, actually you can do this model free, but you have to calibrate it once, right? You have to know, given this parameter, what's the distribution function. And then if you have these distribution functions, then you can do this maximum likelihood estimation. And if you can measure it, then you do a model, get probability distribution functions, and then you can compare.
And then you throw the theory away.
The theory. Yeah, I mean, this is also testing a theory, yeah. But that's a little bit of problem, inverted comma. This is not the historic physics. You look at nature and ask, what does nature tell us? This is more having a model. How can I torture nature such that it behaves like my model? and so this is the hard work. And that's why we don't test models yet. But indeed, one might wonder at what level of precision of these measurements can you start to test models? But they will be very simple. They will be more condensed matter kind of models, which we know are anyway approximations. The question is, when do they break down? It's not about Higgs, for example.
Okay, my question is what you believe to your thoughts in general. I know that this kind of behavior can be applied for atom lithography. Could you comment a little bit on this?
Yes, I can. This is a historic question for me, yeah. Because when I came to Constance, I had to do one experiment, finish it off, which was called atom lithography. So now I don't know what I should do. I can't be very. Let's be neutral.
Do you believe it?
Yeah. It's a question of what you call lithography.
You can switch off the camera.
Also, ja, genau. No transmission to outside world. No, okay. So, it's hard. That all what you could do is periodic structures, up to quasi-periodic structures, but you cannot write circuits. Okay, so now for certain applications, this might be well enough. Okay, and essentially how it works is clear. Yeah, you take this, you lose light and manipulate your particles to get to the right spot. And what you can do is you can just focus it with a harmonic potential, inverted comma, and then you get spot sizes of, I don't know, 20 nanometers or something, what we got at that time. But this is always periodic. Or maybe, now it was 50 nanometers. It was chromium. It was specific because you need the light force to be resonant. And then you have this periodic structure. And then you can try to think of what can you do with this periodic structure. There are different ways. Plasmonic might be a way, but there are other ways of structuring plasmonic parts. Much simpler than taking chromium, which is moving while you deposit it. So my opinion about it is, I'm not so convinced that this is something useful. I'm convinced that it's good, I lived from it, I also sold it, I got money for it. Because I said, well, I can make the best rulers you can think of. I can do a ruler with the precision of the light, and the light is the best measured frequency we know. So I take a frequency comb, I produce this lattice, and then I know I have a lattice with this period up to the 8 digits. Okay, but who needs it? There are other things much better used and much more robust. And I'm sorry, I don't know if this was a little bit a colored answer. Yes.
I want to make sure that I got the right message in the talk. So when you showed the potential there, you transform in a double well.
Yes.
You're essentially changing the K of the harmonic oscillator, right? That's when you get the squeezing from.
The K.
Yes, for instance, you have first the harmonic oscillator.
Yes.
If you translate that to classical mechanics, you just have a specific K, which is the constant y in the oscillator.
Yes.
You do the double well.
Yes.
Change the K.
Yes.
That's where you squeeze.
No. No, because that's on a single particle level. So the squeezing here is really the quantum part of this optics. It's about particles are getting correlated. And the harmonic oscillator here is only used in, it's just used to have something like 2 modes. So you have to define first your modes, and then you put your excitations onto your modes. In our case, the excitations are the atoms. And so this was used in order to get 2 modes, which you can distinguish. And the important thing is it doesn't matter what kind of modes you take. It might be internal degrees of freedom, like levels, and then you're spatially in 1 mode, or spatially in 2, then you're internally in 1. And so at the end what happens is, the important part is that you go, the next step, that you have many particles in these traps which interact, or in these 2 modes interact. And then as soon as the interaction comes for free, because they are not uncorrelated anymore, and this correlation is exactly what this squeezing is about. And the double well was more like used as a tool to get these kind of 2 modes. And all the description I gave at the end were in this limit. So there are much more because they can still move. So it's an approximation. Yes.
I want to make a general question. So are you somehow limited by the atomic species that you're using? So maybe if flying lasers wouldn't matter at all, I think would you prefer to go to another atomic species?
Yeah, that's
it. Because it's so well controlled that you mentioned it as well. I think we have all the stability there in the experimental setup. But if you could maybe solve these problems also by other atomic species, maybe for ultra precise atomic interferometry.
Yes. Yes, that's a very good question. And I think then one should The question is what you want to optimize. Rubidium is a good Yeah, exactly. For example, I mean, conceptually, this applies to everything, every other atom, the concept. Now, what you choose depends on what you want to measure, I guess. And then rubidium is very special because it has these very special collisional properties which are on your side, and we have to fight that we get this interacting, which I didn't tell. But and so it's a question of what you want. Yeah. Essentially, there are better atoms most likely, but I don't know them, and I don't care too much because we are at the moment at this point where we need this control in order to get there, and then the losses, and this is actually the killer, the losses are for rubidium already very small. And they will be very similar to for all alkali atoms. And then if you go to others like strontium, for example, it might be different, but then you have to get the whole thing again set up. So that's a very profane answer. and direct what we can do tomorrow. But if you want to choose your atom, you should choose it first what you want to measure. And then this thing here is then the last step. If you are stuck with the number, then you can try to do these additional correlations.
One question, yeah.
You mentioned you can do that with, in principle, can do any atom, but you need BC, right?
Yeah, that's a good question. Yeah. This is a question. This is also not so simple to answer. If you want to have it simple, then the BC is the best choice because you are stuck with few modes. If you go to more general to many modes, and if you're above DC, you have as many modes as particles, because your occupation number per mode is about 1, then it's not obvious that this kind of squeezing in internal degrees of freedom still converge. For example, there are ions, like you wrap them, you can see them individually. They are exactly a little bit like above DC. But then you can make long-range interactions between them. Okay? So the spins get correlated. And now if you take an image of the whole thing, not resolving where they sit, then again they're indistinguishable, and then you get the squeezing. So at the end of the day, it's a little bit, it's not so easy to answer. It depends at the end what you look at, if you can see this. On the individual one you wouldn't see it, but on the global one you can see it. But then, you know, the other things which I didn't talk about here, about this kind of entanglements, this is a witness for entanglement, then you need some assumptions about where the particles sit, and there you need this occupation number, it's 1 mode. If you go to n modes, you cannot say much. But for using it, and there are examples where you do the interaction via photons, the atoms there are hot. Hot is maybe relative. It's like they are maybe, I don't know, 100 microkelvin or something. They are hot, but still you can squeeze them internally. And there are also experiments, but they are done differently. They are not via collisions, but via this photon-atom interaction. And the collisions in the regime what you suggest in high temperature would be also not on your side, because they collide not so often. You need a high density too. And so now we get into the details, because at the end of the day you have to ask how, I just told you I can do it, but I didn't tell you how I do it. It was more the entertaining part. But if you go closer and look how you do it, there are time scales in your system, how fast you can produce these correlations. And there are other time scales which kill your correlations. And so there, actually density enters critically. You need high enough density collisions that this happens. And so if you go above DC, we could not do the experiment because the density would be too small. But conceptually, although it might take very long and you have to fight the details of the experiment, it's possible also to do above DC. Yes, but all the statements will be more tricky, and it will be much harder to get it. Yeah.
Okay, so I see for the moment all questions being answered. So let's thank Markus again. Thank you very much.
Thank you.